Alright, so last time we were discussing various O-minimal structures. Let's say a bit more about that. So we had a semi-algebraic structure. Plus times and less than, but also remove the less than if you want, it's recoverable. And we had our X. So let me just say a little bit more about this structure. So we showed, and we'll sketch a proof, maybe this class, that the way you prove that this is O-minimal is you show that you have elimination of quantifiers. Everything can be written, if you include less than, everything can be written just by finite number of inequalities and equalities of polynomial equations. So that's not true, it's known not to be true for Rx, but it is known that Rx is what's called model complete, which means it can be defined with just existential quantifiers. So, something is definable in Rx if A can be written as following way. To a set of points, there exists a bunch of yi's, and then you have a formula in the x's and the y's. In other words, you don't need operating chains of their existence for us. You just need their exists, or said geometrically, you just write down a bunch of equations inside some high dimensional space and project them all down at once without doing any Boolean operations in between. So it's sort of a weakened form of quantifier elimination. So this proof is quite hard, substantially harder than this one. And it's also not totally clear why this implies O-minimality. So you sort of have to do a lot of work. There's a nice... Yes?
Phi is a polynomial?
Phi is not a polynomial, but phi is a polynomial inside in the variables and their exponentials. Mm-hmm. I mean, phi is really a Boolean combination of such things. So the nice corollary to Rx being definable, which was its Diophantine, and fits into his theory of polynomials. It's sort of a corollary, but he did a bunch of work first, and then inspired to work on this, and then inspired stuff back. So he proved the following theorem. Suppose you have a bunch of polynomials, real polynomials. Let me say R polynomials and S variables. And we're not going to bound the degree of these polynomials, we'll just bound the number of monomials appearing in every polynomial. So each Pi is a sum of at most n monomials. Or your allowed coefficients as well. Okay? Then if you let x be the zero set of all of these polynomials, then the number of, let me write it as the size of pi 0x, the number of connected components that x has, is bounded above just by a function of R, S, and capital N. Okay? In particular, not referring to the degrees of the piece, right? If we bound the degrees, then Bezout's theorem gives us this basically, not quite immediately, but pretty close to immediately. The point is we aren't bounding degrees. Also note this is sort of extremely false over the complex numbers, right? If you look at x to the n minus 1 equals 0, that's only two monomials. If you have n different solutions, they can get arbitrarily high. So the proof is very simple. So Volog, we can only look at, we restrict the solutions where the little xi's are positive, because we only have, now we have 2 to the s different chambers to consider. Just look at this one and write x to the x sub I is e to the power of y sub I. And the point is that a single monomial in the xi's can be written as e to the power of some linear combination of the yi's. And so now we can allow the ai to be reals all of a sudden. Think of them as variables, we get something definable now in Rx. So as the degrees vary, we get sort of a definable family of varieties inside Rx. Okay, so now we just use cell decomposition. So Rx an O-minimal structure. We can break up the family into finitely many cells and just count. Okay? So, I hit the hard part, which is here. Sure. Uses the O-minimality very strongly. I also think Khovansky managed to get, we don't get it for free, but the growth of this can be arbitrarily large in a very O-minimal structure. But I think he actually managed to get some control over this function in the case of Rx. Okay, so let's do a couple more O-minimal structures. So if S is a structure, then we say that sequence of functions with length k is Pfaffian over S if there exists Pij from R to the n plus k to R, which are definable in S, such that, so you want all the partial derivatives of your sequence to be definable in terms of your structure. Of x, that's an n-dimensional variable, together with all the fi's. In other words, the sequence satisfies the differential equation definable over your structure. Okay? So notably, if f1 of x is e to the x, then you know df1 by dx is just f1. So in particular, e to the x is Pfaffian. E to the x is Pfaffian over just R, well, with nothing else. Let's say it's algebraic. Yes, there was a question or a mistake?
An ultimate line, K is an I, right?
K, I don't think so, right? I want to say that if you differentiate any f by any x, then it's a function of the x's and all the f's. All the f's, yes. Mm-hmm. So it's not like an inductive chain or something. I'm sorry?
It's not triangular.
I don't think so. Did you know it to be triangular? The notes I read did not say that it was triangular. Well, if you were triangular, then you don't need chains of length k, right? You could do it with one function at a time.
Yeah,
So to speak.
true.
Right. No, so I think they do want to include these
It's not
multi-systems.
quite sure you can go thoroughly. Come back to the
All right. Well, I'll say the theorem now, and you can tell me if you know it's false. I'm sure that the book I was reading does say this, but I didn't go into any of the proofs, so.
this point is just calculation.
Right. Nothing can be wrong now. Well, so the point is that theorem due to Spizegger, is the spelling, which says that if S is O minimal, then so is the Pfeiffian closure of S. So if you throw in everything, all the F's which are Pfeiffian for S, that remains O minimum. So is it wrong now? You think you want to do triangular chains? Okay, so maybe this is Fi. Who knows? But okay, so take it with a grain of salt if you're going to use this theorem in your future research. Okay. A little bit odd. Yeah, okay. Alright, well I'm not going to say much more about Pfeiffian, guys, so let's just move on with the question mark. So one function, another category which is very relevant to us is restricted analytic functions. So we say that the function from a closed box into the reals is restricted analytic. If there exists an open set U containing the box and the real analytic extension F tilde from U to R. If you want to allow analytic functions as long as they extend a little bit. In particular, you can't just take a power series on a unit disk with radius of convergence exactly 1. That's not allowed. It has to converge a little bit below, a little bit beyond 1 for it to be restricted analytic. Okay? And it's sort of clear you can't allow that because you don't, if you allow that kind of thing, you could have analytic functions with infinitely many zeros inside the unit disk with radius exactly 1. That automatically can't be minimal because you get an infinite discrete set. So you need to somehow tame your set of analytic functions somehow. Okay, so then Rn is the structure R with plus times, which are already basically kind of forgettable from there, and all these F's. F, which is restricted analytic. And when I say at this F, of course, I just mean at their graphs, extended by 0 or something. And so then theorem due to Vandendries, based on work of Gabrielov, is that Rn is O minimal, and actually the structure is polynomially bounded. So all graphs of one variable functions are bounded by some polynomial, by some power of x. Okay? And what they basically do, or this is one of the proofs available now, is so if you define D you sort of allow division as an operation kind of. So you have the graph of x over y cut off between 0 and 1. This is obviously definable already in our semi-algebraic, actually, right? But if we add this as a predicate, so as like a concrete operation, then we have quantifier elimination. In Rn together with D. Okay. So just like before, right? We don't need the Lesson operation for our semi-algebraic, but if we don't include it, then we need some quantifiers. Likewise here, we don't need to add D, we already get it from here using quantifiers, but if we add it to the basic predicate, then we have quantifier elimination, which immediately implies the minimality statement. All right, and finally, there's a theorem of Van der Dries and Miller, which says that if we take Rn and we throw in x, then this structure is homonym. Okay. So this is, as I said before, this is the structure we're going to use for basically everything we do so far. And see, I should mention that Wilkie proved that it's not true that if two things are O-minimal and you join them, you get something O-minimal. So there's counterexamples to that statement. So this isn't just a consequence of the previous theorems. All right. Questions about any of these results? Okay, so let's just list some corollaries of the type that we would need for unlikely intersections. So, if you look at the exponential map, even the 2 pi I z, we could remove the 2 pi I obviously, but it's nicer this way. So this is obviously not O-minimal anywhere as before. But now if we let F be the subset, so Z and C, such that the real part of Z is between 0 and 1, then e to the Z restricted to F is definable in Rnx. So this merits a word of explanation. We've been defining definability as being inside powers of R, not powers of the complex numbers. So whenever we say this, we just mean we identify C with R squared and C to the n with R to the 2n, and then it's definable inside regardless. Okay. So this is definable in Rnx. Why? Because if you look at e to the x plus iy, this is e to the x, and e to the x is fine because we have x, times e to the iy, which is cosine y plus I sine y. These guys are not fine, but if you restrict them to the interval 0, 1, then they are fine, because the arbitrary is analytic. So cosine is not fine on the entire real line, but it is fine on an interval. You have Rn. Okay. So this puts us in the world we want. If A is an abelian variety, and we look at the uniformization map, Cm to A is the uniformization of A. Again, pi can't be definable, but if we let F be a fundamental domain, so a fundamental parallel biped, or however it's spelled, then pi restricted to f is definable. In fact, it's not just definable, it's definable in Rn. We don't need x here because it's already analytic and it's a compact set which extends beyond it on f. So there's a brief question of what this means because A is it's not a power of R, it's not R, it's just some complex manifold. So to properly make sense of this, you take A, you embed it in some high-dimensional projective space, and then the graph there is definable. So there's like a bit of work to do, which I'm not going to do, to sort of define precisely what this means, but I think the idea is sort of easy to understand. Now let's look at the J function. So here's the fundamental domain, which we're going to call F. And so now claim J restricted to F. So J, which maps F into the complex numbers, is definable in Rn. I think you need Rnx for this. Maybe I'm wrong. No, I think you need Rnx for this. Well, let's see. The proof I wrote down is Rnx. So what's the point? So first you take F. Yeah, you do. And you map it to the disk via Z goes to e to the 2 pi I Z. Yeah, and if you're going to do this, then yeah, so you need the exponential function on the entire. Sorry, so e to the 2 pi I Z, right? So I Z lies inside the negative reals, so you need the exponential function inside on the negative real line, which is not in Rn. So this is definable in Rx, and then D goes to C is sort of is Q goes to J of Q, right? So J has a power series in Q of radius of convergence 1. So this is not actually definable. It's analytic, but it's not definable because it doesn't extend beyond the disk. But if you look at the image of F in the disk, it looks like this. It doesn't actually approach the boundary, right? The boundary is the image of the real line in the upper half plane, and the fundamental domain doesn't touch the real line. So on here, it is ultra analytic. I mean, technically it's meromorphic, so you can multiply by Q first or something particular like that, but that's not a big deal. Okay, so this is good in Rx. Actually, this needs Rnx already, and this needs Rn. Because you have restricted sign and cosine here as well. Okay. Here's the kind of thing that we want. And so then, I'm not sure if I use it in the class, but Fedorsov-Starchenko is the case of AG, and in general, Klingler, Umo, and Yafev using toroidal coordinates showed that if this is any uniformization of a Shimura variety S, and F is a fundamental domain, so one of the usual fundamental domains, then pi attributed to F is definable in Rnx. And you can add the word mixed, and then that puts everything all down in the same framework. So the point being that you always have definability when you need it in this context that people study. All right. So yeah, we'll start up on using this next week. Right now what I want to do is I want to give an idea of how you prove the Tarski-Seidenberg theorem, just so we see homonormality done in sort of the simplest case, or how you might start with it. So yeah, what we have to do to prove the Tarski-Seidenberg theorem is to eliminate quantifiers, which means, what's the canonical case? It means if we have some like two-variable polynomial, p of xy, then we need to understand for which x, p of xy has a solution in y. We need to use some decision procedure to decide if p of xy has a solution. And so this is done using what are called Sturm sequences. There's many ways to do it, actually. I think the original one, and it's pretty simple, is Sturm sequences. So I won't give the general case, but rather is it the following thing. So suppose that p of x is some polynomial. We want to understand how many real roots it has. So what we do is the following thing. We set f0 to be p of x, f1 to be p prime of x. Okay? And then we set fi plus 2 to be minus the remainder of fi by fi plus 1. So in other words, fi plus 2 is fi plus 1 times r of x minus fi, where r of x is just some polynomial, and the degree of fi is at most the degree of fi plus 1, is less than, the degree of fi plus 1. Okay? This minus ends up being important, we'll see. Okay, so then we have f0, f1, up until fk, which equals 0. Eventually this can become 0 because degrees keep dropping. Okay, so I'll do an example in a second. So the following, you do the following thing. You define vf at a to be the number of sign changes in the sequence f0 of a, f1 of a, and so forth. Okay? So every time it goes from negative to positive, you sort of count that as a sign change. And to do this, you sort of ignoring zeros. So you remove all zeros from the sequence, and then you count the number of sign changes. Okay? And the theorem is the number of roots of p of x in the interval AB is v of A minus v of B. Okay? And so, sorry, this is an open interval. Apologies. And you can also allow A to be minus infinity and B to be infinity. Right? Because as you go to minus infinity, as you go to infinity, what your sign is just the sign of the leading coefficient of your polynomial. So you can define it that way. So you can extend this to minus infinity. Let me just do an example. There's nothing super tricky about this, but it's helpful to see it done out. Let's do like x squared minus 3x plus 2. So then f0 is x squared minus 3x plus 2. f1 equals 2x minus 3. f2 is, so we, divide this by this and take the remainder. So let's see. Should have planned this out better, but I didn't. So let's suffer a little. So we have an x over 2, minus 3x over 2, minus 3x over 2, minus 3 over 4, plus 9 over 4, minus 1 over 8. Does that seem sort of reasonable? 3 halves? I think that's reasonable. Let's go with that. No, sorry, minus 1 over 4 is what I mean. So f2 is 1 over 4, and then f3 is 0. Okay? So then let's take the interval, let's let a be minus 2 and b to be 3. And we should get the answer 2 at the end, because we have the zeros 1 and 2. So let's see, at minus 2, f0 is 4, let's test this at 12. This guy is minus 7, but we have a quarter at 0. So here we have 2 sign changes. And b equals 3, we have 9 minus 9 and 0, so 2, and then 3, and then a quarter and 0. So, VP, sorry, it should be VP, right? VP of 2 is 2, and VP of minus 2 is 2, and VP of 3 is 0, and 2 minus 0 is 2. That's what we desired. So it worked. What's that? Okay. So is the statement example sort of clear? I'm sorry? No, the proof will show it is, but it's not, well, I don't know. It's not until you prove it. A priori, I can't see why it's so obvious. Okay, so let's get the proof. So first assume f is square free. Not hard to reduce that case, and I don't sort of want to deal with trying to log it. So p is square free. Sorry. Assume p of x is square free. Okay. So note that the function vp of x is constant unless away from the roots of the fi, right? The fi don't become 0, they're continuous, so nothing changes, the number of signs. So what we're going to do is figure out what happens at a root. So suppose fi of t equals 0 for some I that's bigger than 0. So remember that fi plus 1 of t equals some r of t, fi of t minus fi minus 1 of t. And so these guys have opposite signs. This is a 0. Right? So the sign of fi plus 1 of t is negative the sign of fi minus 1 of t. In other words, the sequence goes from like plus minus minus to plus plus minus as you cross t. Right? Because this guy, these two opposite signs, this guy changes signs. So you have a total of 1 root change, 1 sign change in each case. Okay, so this is good. Nothing happens as you cross the 0 of a guy inside. Also, in this case, by induction, every consecutive guy is relatively prime. And so you don't have to worry about 2 guys in a row being 0. It doesn't happen in this case. Okay, so now what happens? So suppose that f0 of t, which is just p of t, is 0. So it's a simple zero, so what, I mean, you get either this case or this case, right? So if P goes from negative to positive, P prime of T is positive, and if P goes from positive to negative, P prime of T is negative. So in this case, you go from minus plus to plus plus. In this case, you go from plus minus to minus minus. Right? This is F0 and F1 are P and P prime, and so here it was P is negative and P prime is positive, and here P is inverse. And so VP of X drops by 1. Okay, that's the proof. So it's not actually difficult. It's kind of inspired. It's not that difficult. But it's kind of neat, right? If you have a real polynomial now, even with like weird coefficients, all you do is you form the sequence, you count the number of side changes and leading coefficients, and then you get up to the plus infinity and subtract less number of zeros. Great. All right. So we need a slight strengthening of this. I mean, we need a few slight strengthenings, but I want to give one which is sort of essential. So the other thing we might want, and we'll see in a second, is if we have two polynomials, P of T and Q of T, and let's assume again for simplicity that they're square free and relatively prime. That sort of leads to more steps in deduction, but it's not essential. So we might want number of zeros of P where Q is bigger than 0. This is the kind of thing we might sort of get at with our semi-algebraic conditions. Then we let F0 be P. This is a bit weird. We let F1 be P prime Q. So F1 is of a higher degree than F0. Then from then on, we do the same stuff. So you know, if they have any degree at all, then F2 is going to be minus P most likely. But then we'll start going down in degrees again. And then you define VPQ of X to be the number of sign changes. Again, in this sequence now. And so then, theorem, take Ausdrucksturm, that VPQ of A minus VPQ of B equals number of zeros of P where Q is bigger than 0 minus number of zeros of P where Q is less than 0. Okay? And the proof is the same. Basically anything inside the sequence doesn't contribute. And now if you do the thing for a 0 of P, well, you know what the P prime thing is, but then Q might flip you, right? If Q is negative, then instead you go from minus minus to plus minus. You gain the proof instead of losing it. But it's the same proof. Okay, so as a corollary of this, if you look at if you let R of P and then a bunch of Q's be sort of VP minus VPQ1 minus VPQ2 minus VPQR and then plus VPQ1Q2. So sort of you subtract all the 1s, add all the 2s, subtract all the 3s, and so forth. Then this function of A minus this function of B, I believe should be like 2 to the R times the number of zeros of P, where all the Qi are bigger than 0. Sorry, am I writing too messy and small? I'm just subtracting this function at A minus this function at B in the interval AB. Sorry. Basically, if I insist on zeros only where a bunch of polynomials have a specific sign, I can recover it from this kind of procedure. Okay? And let's just follow from here. Yeah. Sorry, this is the way I wrote it. No. This is, and these are all pluses. I'm sorry. Yeah, you add them all, right? If all the q's are positive, just get this guy. So the point is that these terms are cancelled, right? Like if q1 and q2 are opposite signs, then you come up with a plus or a minus an equal number of times. Okay, so now, so proof of Tarski-Seidenberg. Skipping a whole bunch of steps. So we want to eliminate quantifiers, right? And it's enough to eliminate existential quantifiers, because the for all one is Boolean operations of those. So suppose we'll eliminate quantifiers one at a time. So suppose you have a quantifier that exists y such that sort of P1 equals PR equals 0. And then you have a bunch of polynomials which are bigger than 0, where the x is in some n-dimensional space. Okay? So look at this set. And what we want to show that we can define this set without this there exists y. I just want to reduce it. We want to show this thing can be defined just by writing these kind of conditions in the x's. And that will eliminate this quantifier. Yes, there is a y. Sorry. There's a y in all of these. I thought I did my job when I wrote there exists y. Okay. Yeah. We want to show that we can remove all the y's here. And just have equations of the x's defined set directly. And so then in general we have we start with a chain of quantifiers and we can peel them off sort of one at a time. Okay. So first of all, so this is let's say there's R of these and I don't know, S of these. So in fact you can assume that R is 1. So if we let P just be the sum of squares, right, then all the PI's are 0 is equivalent to P is 0. So we can assume this P is 1. And so now the point is you can use, so what we want to do, we want to we want to count exactly those x's for which this polynomial P, we replace this now with P equals 0. For which this polynomial P in y has at least one 0 where all the q's are positive. Right? But the point is we can write the Sturm sequence parametrically in y. It's just a matter of taking remainders. Right? So what you do is you define the Sturm sequence P of xy. F1 is P of xy, some product of the q's of xy, the prime here. This is d by dy, and then so on with the remainders. And then sort of what we want is something like v p cubed of minus infinity minus vp cubed of infinity is greater than 0. But what are these two quantities? They're just measuring a bunch of sign changes, right? So we can split this up into the precise locations where the sign changes. Precise locations where the signs are in fact determined. So you write semi-algebraic conditions, sort of specifying the exact sign of every point inside here. And these end up being semi-algebraic conditions exactly in the variables x, because the coefficients of the leading degrees of the y's are polynomials in x. Okay? And so then you have sort of finitely many possibilities, and you only want to look at the ones where this difference is bigger than 0. Each of those defines a semi-algebraic condition on the x's, and so you've gone down from this sort of expression to just a bunch of conditions on the x's. That's to eliminate that quantity. Okay, so there's sort of details to fill in, but I think this is the main point. You have to be a little careful, right? Because to divide through, you end up getting some denominators and stuff. The x's, you gotta clear those. You have to be careful that things are actually co-prime, and where they aren't, that puts you in some lower semi-algebraic set. So there's a bit of sort of bookkeeping with the deduction, but this is certainly the main step of it. Any questions about this very loose sketch? All right, so I think we're done with homonomiality. So next time we'll start improving on reward for reals. Thanks, guys. Oh, and there won't be class next Friday or the Monday after that. So we'll have 2 consecutive days of no class. I'll announce it again if that was confusing.